let's talk about what people have questions on. So I think the first thing that was brought up is WTF, which of course stands for what's the flux? So, all right, so we should probably talk about that. So what does this mean? So this is, in particular when we talk about flux, this is a flow through a surface. And so if you don't like saying the word flux because it sounds like you're saying something you shouldn't have said, just say flow. What's the flow? So in this case, how do you find it? Well, we're doing a very, very special case. So right now, we have the following case that we can handle. And the way I phrase that thinks, ooh, does that mean we're going to learn something to help us do more complicated cases? And the answer is yes, after the exam. It's going to be cool. But that means for right now, we can only do simple things. So what's the simple thing? So the simple thing is we have some surface floating out here in three-dimensional space. I don't know what it is. Apparently it's a potato chip the way I've drawn it. All right. But what does it look like? It's z equals f of x, y. And where is this surface? Well, if you were to look down, you would see here there's a shadow in the xy plane. So this shadow that we're talking about, this is the region R. So when we ask about questions about flux, the only things we can do right now is we're doing the flux through the surface that has the form z equals f of xy over some region R. Now, that's part of it. Now that's just the surface. We haven't talked about the flow yet. And so the other thing we need, there's two more things you need. You need to know what's your surface. You need to also know your orientation. And most of the time, we will specify. You look for the words upwards or downwards. 99% of the time, it's upwards. So that's what I'm going to focus on. And when we talk about orientation, we mean the surface has an orientation. So that if you were to look at any particular point on the surface, I could be perpendicular to it in one of two ways. I could either be perpendicular, generally speaking, going in an up direction, or perpendicular, generally speaking, going in a down direction. But the default is up. So that's the formula that we're about to write down. So you need to know the surface, you need to know the orientation, and the last thing you need to know is the actual flow function. So it's given as a vectored valued function. So you're looking for a vectored valued function, and you read off the pieces. It might be written as MNP, it might be written as MI plus NJ plus PK. Those are the two different ways that we tend to write these things. Now, if you have all this information, then the answer to how do you find the flux, the formula that we throw around to be theoretical, it's the surface integral of G f dot n dSA. But that's not how you actually use it. What you do is you convert your surface integral into an integral over R. So instead of working on the surface, you work down over R. F dot n becomes minus m f sub x minus n f sub y plus p. And then you have dA. So this is the formula you'll need to remember. One small caveat to this formula is you might need to update your z's. Now, when I talk about updating your z's, what I mean here is that your functions m and p, these are vectored value functions, and they depend on where you are at in space. They could possibly have a z value in them. If they do have a z, just replace anywhere where you see a z by a function, f of x, y. So pretty much any question that you're going to see right now which involves flux of a surface, if you can remember this formula, you're good to go. So let's just do the dangerous thing and do something fairly benign. We'll do a simple surface, and we'll see what happens. Please be a simple surface. All right. Well, let's see, what's a good simple surface we can do? Well, here's one we don't see very often. Suppose let's see, is this going to work? No, that's not going to be clean enough. Never mind, we're not going to do that surface. Do you have a favorite surface? All right. Let's do find the flux. We'll do f of xy. We'll have it be a hyperbolic paraboloid. So we'll do x squared minus y squared. So that's our surface. Oftentimes we don't write f of xy. We normally write z equals x squared minus y squared, and we just know that when we see that f of xy is x squared minus y squared. So the flux is through this surface. Now this surface is, of course, defined over everything, so I have to specify a region R. So let's suppose R, where R is the quarter of the unit circle with x and y greater than or equal to 0. Okay, so there I've now specified my R. So I have my surface. I also am going to say I have upward normals. And if your problem has downward normals, it's easy to fix. It's an orientation. And anytime you have an orientation issue, just put a minus in and you fix the orientation. So we find the flux, we have our surface, we have our upward normals, and we're going to say that F is equal to x comma minus y and 4. Yeah, that's perfectly fine. Okay, so given all this information, what do? Well, we apply the formula. So the flux is going to be the integral over our region of minus m fx minus n fy plus p dA. Now, how do we actually do this? Well, it's a quarter of a unit circle, so we should probably switch to polar. And if you ever see things where your boundaries are polar, you should say, okay, when you see boundaries which are circles, polar is the natural thing. You should almost automatically see, like, ooh, circle, I should think polar, because most of the time, you're right. And so, if you see a circle, think polar. All right, so we're going to do this in polar, all right, which means we need to update. So we're going to go through minus, the m becomes x. What is f sub x? 2x. Then we have minus n, that's minus y. What is f sub y? Minus 2y. Plus p, which is 4. Now you might think, well, why doesn't p get multiplied by anything? And actually it does. It gets multiplied by 1. But usually we don't write multiplication by 1. So again, once you know the formula, it's just, okay, make sure you know how to plug the pieces in. And now that's what we're integrating. We're integrating this dA in polar, r dr d theta. And then, okay, we're the unit circle, the first corner. So 0 to pi halves, and r goes 0 to 1. Well, wait, we can't do this yet. We gotta switch things. We haven't put this into polar yet. So this becomes 2x squared and negative 2x squared and minus 2y squared. So what did we get there? Minus 2r squared. Yeah. So 0 to pi halves, 0 to 1, 4 minus 2r squared times r. So I guess I could say 4r minus 2r cubed dr d theta. Now you can break this integral up. Integral 0 to pi halves d theta. integral 0 to 1, 4r minus 2r cubed dr. Well, the first integral, that's straightforward. That's pi halves. The second integral, that's 2r squared minus 1 half r to the fourth. And evaluate from 0 to 1, which gives us 2 minus a half, which is 3 halves. Okay, so this bottom part here is 3 halves. So, whoops, there we go. Pi halves times 3 halves gives us our final answer of 3 pi fourths. Now, if we get a negative answer for flux, what do? The answer is we don't care, because flux could be negative. So don't panic. Now, if you're nervous because you're like, but our teachers are such optimists. They always like positive answers. Well, maybe not. Sometimes we write these problems and don't actually check the answers, and then we get to them and say, boy, we should have really chosen this better. So don't panic if you get negative answers for flux, because it is possible to have negative flow. All right, so there's an example of flux. Let's do an example for UV substitution. So a perennial challenging type of problem. So compute the integral 1 to 2 x squared to 8 minus x squared of 8x e to the power y plus x squared squared minus 4 times y plus x squared dy dx by changing the variables. All right. Now, let's think about this. And this is a fun problem. I think this came from an old final exam, where by old, I way back in 2017. Oh, wow. It was archaic. You know, how did people even live back then? All right. So it's helpful to sort of get a quick picture. And problems like these are problems where we like to give pictures, because we want to make sure you have a good grasp. And the picture is really important for this type of problem. Now, let's think about what we need. Whenever you're doing a substitution, a UV substitution, you always need to know the substitution. We're going to give that to you. So don't panic and be like, how do I find it? The answer is you read the problem. And you see, where does it say U and V? And it says, oh, it's right there. Okay, good, we found it. All right. So that's usually not the hard part. So now we go to what is the hard part? Well, the hard part is breaking up and figuring out the 3 pieces of every integral. You ought to go through and do all 3 pieces. Now, what are the 3 pieces? Well, one of them is Jacobian related. And what I'm talking about when I say it's a Jacobian, it's related to the dy dx. How does that translate? You have to account for that. Now, you want to do that first, because the next thing you want to figure out is the function. And the reason I say you want to do Jacobian first is it's possible some of this expression here could get absorbed into your Jacobian. So somewhere in here is the part that we're going to have to translate the function into. And so we're going to have to do that. And then, of course, the last thing you have to figure out are the bounds. And so if we can get the bounds, well, that comes from our bounds here. And we have to translate that into our new setting. So we're going to go through and do these 3 things. So for the Jacobian, so here I'm going to find the Jacobian, which is going to turn out to be a function of x and y. Because what I'm going to do is I'm going to start with u and v. And I'm going to take the partial derivatives and put them into a little 2 by 2 matrix. So u sub x, v sub x, u sub y, v sub y, something like this. You don't have to be 100% correct, because oftentimes, as long as it's kind of reasonable, you're going to get the right thing. So when I say kind of reasonable, you should have, say, your u's and v's in your columns and your x's and y's in your rows. If you do that, you'll get something which is fine. And just remember, whatever you get out, make sure it's positive. So in our case, u sub x will be 2x, and v sub x minus 2x. U sub y is 1. V sub y is 1. So, taking this determinant, 2x minus 2x gives us 4x. Now, how do you read this? This says that dx dy times the Jacobian of xy becomes du dv. So another way to say this is 4x dx dy is equal to du dv. Now, very conveniently for us, we have an 8x, so we're going to take 4x of that and put it with the dy dx, and that's going to become our du dv. So that's helpful because now we say, look, I don't have to change everything for the function. So when I go into my next phase, my function phase, I say the 4x, I'm pulling that off. So my real function is 2 e to the power y plus x squared squared minus 4 times y plus x squared. Now, we have to find a way to rewrite this in terms of u and v. And most of the time, it's going to be pretty obvious what to do. So you're looking for expressions inside of here that look like the substitutions you're making. So here I see a y plus x squared. So I say, okay, great. 2e to the u squared minus 4u. Perfect. Everything's in terms of u and v. I'm done. All right. The function, once you understand the part that actually has to change, that's almost always automatic. So that leaves us with what? Well, now we come to our bounds. So we have some curves here. We have the curve y equals x squared. That's a parabola that opens up. And then we have another curve, y equals 8 minus x squared. So that's a parabola that opens down, but then we shift it up so the intercept's at 8. And, okay, it's coming down. And my picture here is very bad because where would they intersect? Well, they'd intersect where x squared was equal to 8 minus x squared. And if you do this computation really quickly, you'll see that means x squared equals 4, which means that this is at x equals 2. And so our intersection is at 4. And if you look at my picture here, that's not quite halfway. Well, it's a picture. It's just trying to get me an idea of what my region looks like. I'm going between 1 and 2, so if I want an idea of my region, I can put in x equals 1. And so what my region is, in my current integral, is it's this shape here, bounded by these 3 curves. All right, so that's my current region. What I want to do is I want to figure out what's my new region in terms of u and v. So to figure that out, I'm going to go through and look at each one of my curves. So what are the curves? Well, downstairs, this bottom curve, that's y equals x squared. The upstairs, that's the curve y equals 8 minus x squared. And on the left-hand side, you have x equals 1. So those are going to be my 3 curves which bound my current region. Whatever those transform into, those are going to be the 3 curves which bound my region in the UV plane. So I have to figure out what do they transform into. So we're going to do each one of these curves. So let's do x equals 1, y equals x squared, and y equals 8 minus x squared. Now some of these are pretty quick, and some of these take a while. Now, for instance, what do I mean by pretty quick, some take a while? You're keying off of y plus x squareds and y minus x squareds. If you see those, you're happy. You're happy because they're easy to make substitutions in. So, I see a y equals x squared. I say that's the same as y minus x squared equals 0, which means I see a v equals 0. So that's one of my bounding curves. Y equals 8 minus x squared. I say, whoa, move that x squared across. You get y plus x squared equals 8. So that tells us that y plus x squared, that's u, equals 8. And then we get to x equals 1. All right, what's true about x equals 1? Well, let's put in x equals 1. We can say that u is y plus 1 and v is y minus 1. So in other words, we don't get like one simple thing, but we have some combination now. We say, well, it would be nice to get rid of the y's. And so you think of just some way to do that. An easy way to do that in this case, you can do a solve for y and substitute. Here I'll do a subtraction. Subtract both sides. U subtract v. Well, that'll be y plus 1 subtract y minus 1, which will be 2. So these three curves, u minus v equals 2, v equals 0, u equals 8, those are now my bounding curves. I say, okay, good, I'm getting close to the point where I actually do integration. Because it's not just setting up, we've got to compute it. So now we need to get a sketch here in our UV plane. Now, somebody asked me, how do I know which one is U and which one is V? And the answer is, whatever you like. It really doesn't matter. We just go by the convention that U comes before V in the alphabet. So we put U and then V, like X, then Y. It's a choice, and if you make a different choice, it won't change anything. So just make what you're comfortable with. In fact, that's true of a lot of math, is what are you comfortable with? That's the choice you should be making. So some of these curves are fairly easy to sketch. So let's change our color so we can see them a little bit better. If we sketch v equals 0, that's just right down there at the bottom. And u equals 8. Okay, that's a vertical line. U equals 8. And then we have the other curve, u minus v equals 2. It's probably easier for us to read this as v equals u minus 2. So in other words, you swap the u and v. And if you do that, you say, oh, okay, so it's a line that's going up at sort of slope 1, and it has an intercept of -2. Okay, so maybe here's my intercept of -2, and I'm coming up by 1, and there we go. So we can spot a couple of things. For instance, when do I cross? Well, in other words, when does v equal 0? And the answer is when v equals 0, u is equal to 2. How about this point? Well, we know the u coordinate is 8. For the v coordinate, well, put in 8 minus 2. That would be 6. So I'm at the point 8, 6. And so I see that my region here translates into a triangular region there. And now I also see that I've run out of space, even though I'm not done with the problem. But that's okay. We have paper technology. All right, so let's see what we need to do. We need to translate this integral. So we'll make some notes here. All right, so we're going to get an integral. We'll write down our function. Our function is 2e to the u squared minus 4u. So our function is 2e u squared minus 4u. Now, at this point, we're going to be integrating du dv. And oftentimes when you do a substitution, afterwards there's a choice to be made. This happens, in fact, frequently with integrations. We have two-dimensional integrations, which is what's the right order of integration. So in this problem, we have two choices. We could be going du dv, or we could be dv du. And when in doubt, you just ask yourself, well, which integral would I prefer to start with? Would I rather start by integrating with respect to u, or rather start by integrating with respect to v? Now here, it's super easy to integrate with respect to v, because it's all a constant, if we think of it in terms of v. On the other hand, in terms of u, that is not good. We're not going to be able to integrate it. And I know you're thinking, but I'm so creative. I know what I'll do. I'll just write down 2e to the u squared minus 4u, then I'll divide by 2u minus 4. That must be how it works. No. The rules for integration are not nice. That's how we make sure calculus teachers keep their jobs. We have to make them hard. But they also follow the rules. So you can't integrate this in a nice way with respect to u, which means we're going to be setting up for dv du. Now, so that's our Jacobian. Really, we already pulled out the 4x dx dy. We had to choose, was it du dv or dv du? We now know our answer is dv du. So we're left with figuring out, okay, the bounds. So we look at u and say, well, where does u go between? So here, u will start at 2, and we're going to go to 8. So u goes from 2 up to 8. All right, well, what about v? Well, so I have a value for u. V is going to go between these two curves. So again, what is this curve? We wrote it down. It's the curve v equals u minus 2. So this is the curve v equals u minus 2. So we're going to go from 0 to the curve u minus 2. All right, so there's our integral. So now we can start here. Say, all right, this is our problem. So we're ready to begin. We integrate 2 to 8, and you're like, yay, this is easy to integrate with respect to v. Woohoo! V. Evaluate from v equals 0 to v equals u minus 2 du, which becomes the integral 2 to 8 of 2 e to the u squared minus 4u, and then u minus 2 minus 0. Now, these problems, when we ask you to set them up and evaluate it, almost always you should be saying, I suspect that something interesting is about to happen. In other words, that we're being set up that there's a nice substitution to make. So look for good substitutions. And not all substitutions are the same. Sometimes you have to break things apart and use different substitutions in different parts. But here, there's sort of a clear idea of what to substitute. That u squared minus 4u, that's on the inside. Now, I've already used the letter u. I can't use u again. So we're just going to double down and go with double u. And so double u, u squared minus 4u. Now, if we had to do another substitution, we'd go to triple u, which, in case you're wondering what does triple u look like, that's triple u. But we probably won't get there in this setting here. Well, maybe. We'll see. All right. So w is u squared minus 4u. dw would be 2u minus 4 du. And if you look, take that 2, which we've been wondering why that 2 was there. It's just for this moment. Because 2 times u minus 2 gives 2u minus 4 du, which means we're going to get the integral of e to the w dw. Then you have to update your bounds. Plug in 2. You'll get 2 squared 4 minus 8. 4 minus 8 is negative 4. Then you'll get 8 squared, which is 64, minus 32. 64 minus 32 is 32. So you get e to the w evaluated from negative 4 to 32, which is e to the 32, which is an enormously huge number. But not the right answer, because you also have to subtract e to the negative 4. This is super tiny. In comparison of sizes, you wouldn't even detect this e to the negative 4. But it's there, and we found it. And that's the answer. All right. So really, UV substitution problems, it's sort of a process. Understand you have the 3 parts, know how to write the 3 parts, and follow through. Okay. So there was another question, which is, let's do a Green's theorem problem. Now, how do you recognize a Green's theorem problem? Well, we can't afford to actually print in green on these exams, so otherwise we'd probably have fun and like, let's print one on green ink. But, okay, so what's Green's theorem? So Green's theorem, this one is a little bit tricky because there's something you have to remember. What it says is, if I have a region in my plane, it can be any kind of region I want, and I have an orientation, it could even have a hole in it, and just got to make sure your orientation with the hole is consistent. So what the theorem says is that if I want to integrate on the curve of that region, or I should say the boundary of that region, boundary of R, oriented in the correct way. Now, what's the orientation? Just remember the song. To the left, to the left. When you walk the curve, keep the region to your left. Right? What does that mean? It means that if you were standing on this curve and you were following it along in the direction that the arrow indicates, your interior should be to your left-hand side. Okay, so that's what we mean. That's the orientation. All right, so the integral along the boundary of R of m dx plus n dy. And by the way, we can obfuscate this. There's lots of ways we can write this. This can also be written as the integral around the boundary of R of f dot t ds. Or also be written as the integral around the boundary of R of f dot dr. All these things mean the same thing. It's just you're doing an integral on the boundary. It's a line integral with an orientation built into it. Okay, so that's not the part you have to remember. The part you have to remember is that this is the integral over the interior of the region, partial n partial x minus partial m partial y dA. And here's why I say you have to remember something is which partial derivatives in which order. Because there's a difference. There's a sign involved. And when there's a sign, it's like, okay, there's always a danger of being off. And we want to make sure we get our signs correct. Because our goal is, of course, get all the points. We want all the points. So we should get them all. Okay, so that's what we want to be able to do. Okay, so we want to do a problem like this. So we have to start. And let's suppose we have a particular problem. And I hope I'm not going to regret my choices I'm about to make. But let's suppose you say our region R, so R consists of the following. Well, let's do it by picture. It's going to be a square with side lengths 2 centered at the origin. All right? But that's just, we're building it up. So R consists of a 2 by 2 square with semicircles of radius 1 glued on each side. So just when you thought your region was simple, we're going to make it more interesting. So we have this shape. All right, so there's our shape. So, all right, our region. So our region is the whole thing. This is just how we build it up. All right, so what's our bounding curve? Well, our bounding curve is this outside curve that goes over all of the semicircles. Okay, so, and it's oriented the correct way. We'll say it's oriented counterclockwise. Of course, that's a terrible way to say to the left, but that's okay. We'll live with it. Unfortunately, a lot of the mathematicians that came up with conventions lived before Beyonce. So it's a shame. It's a shame. All right. So what's the problem? Well, we want to integrate along the curve the following function. Minus 4y sine squared x dx plus sine of 2x dy. Now where C is the bounding curve. C equals the boundary of R. Okay, so this is a type of problem that you might encounter. So what do we do? Well, first off, okay, how do you recognize these things? Look for a closed curve. Or you see something that says, you're looking for a curve which is a boundary of some region. When you see a closed curve, you should be thinking Green's theorem. Green's theorem is sort of the giveaway. In some sense, we have these two beautiful ideas. There's the closed curve is Green's theorem. If it's not a closed curve, in other words, you have a start point and a stop point, and they're different, and you have some kind of crazy curve in between, then you think not Green's theorem, but you think of, look for potential functions. So if you see a crazy curve with different ends and start, think potential functions. If you see a closed curve, think Green's theorem. All right, so what do? We apply the theorem and hope, fingers crossed, something nice happens. So this will be the integral over R. We take our derivatives, and so we come here, this is our n, and this is our m. Derivative of sine of 2x to cosine 2x. All right, so this is our n sub x. Then we're going to subtract our m sub y. So what's the derivative? Minus 4y sine squared x with respect to y. Minus 4 sine squared x. So that's sort of another clue is, in some sense, when you see complicated functions in this line integral, it's a sign that says, please don't try to actually do this line integral the way it looks like you were asking you to do it. Please do it the other way. Because oftentimes complicated functions, when you take those partial derivatives, it's like, whoa, they're gone. And that's what we like. We like things to disappear. But how do you do this integral? Integral of 2 cosine x, integral over the region 2 cosine of 2x plus 4 sine squared x. Is this integral something that we can actually do? Well, suppose this was on a test, because I could imagine something like this being on a test. And we said, actually find it. How would you go about doing this integral? There's a suggestion from the back.
Power reduction.
Yeah, so power reduction, which you can also think of as, there's lots of identities that basically they're all just like, I have one idea, but I'm going to call it 6 different things, so it makes it sound like I'm important. So power reduction, okay, so power reduction here, because you never work with sine squared, what do you work with? Well, you work with 1/2 minus 1/2 cosine 2x. Yes? Yeah, you do. It's a true story. Okay, that's power reduction. Well, notice what do you have here? This first piece is positive 2 cosine 2x. When you distribute the 4 through, what do you get? Negative cosine 2x. It's almost as if we wanted something great to happen, because we did. In this case, the cosines disappear, like you're integrating 2. Well, integrating 2 is the same as saying twice what you get when you integrate 1. Well, what do you get when you integrate 1? You get area. So, our answer is going to be twice whatever the area is. So now we say, well, let's look at the picture and use some geometry. Geometry is really important. Look for circles. Look for rectangles if you can. Or maybe if you're in 3 dimensions, cylinders and spheres. So here, well, it's a square. How much area is in the square? 4. Plus, we have 4 half circles. Well, 4 half circles makes 2 whole circles. All right, well, how much area is in 1 whole circle? So this would be a circle with radius 1. It would be pi r squared. So that would mean I have 2 full circles, so 2 pi. So the answer is 8 plus 4 pi. And this is the kind of question that you might see. Now, sometimes it won't be as easy as integrating just a constant, but it won't be far off. It'll be something that's relatively easy to integrate. All right, so that's an example of Green's theorem. Okay, I'll do one more. One more example. So find the surface area for the solid bounded by the surfaces z equals 4, x squared plus y squared equals 1, and z equals x squared plus y squared, which has density delta of xyz equals 4. All right. Well, we should sort of try to understand these things. All right. So we'll get a rough sketch. And again, on an exam, you wouldn't have to do a rough sketch. Something like this, we would give you a picture. But we're here. We can handle a few basic things. Do we know what z equals 4 looks like? It's a plane. It's a very, very plain and simple type of surface. So I have this plane up here at z equals 4. All right, that's good. Good to recognize different things. How about the surface x squared plus y squared equals 1? All right, now you say circle, you're thinking 2-dimensionally. It's a circle in the xy plane, but when I say x squared plus y squared equals 1 in 3 dimensions, what do I get? Cylinder. Because it's a circle, but you just copy the circle for every value of z. So it's always the same circle up and down. So there's this cylinder floating around here that goes up and down. Well, it goes up and down forever, but probably we're not going to have to go up and down. All right, forever. And then there's the last surface, z equals x squared plus y squared. What does What does that look like? That one, you're going to see this one so often, you should recognize it. It's a bowl. Now, if you want to be fancy and use a fancy word, you can say paraboloid, or if you want to be really fancy, elliptic paraboloid. But look, we know what you mean. You mean bowl. Okay, so it's a bowl. So this is a bowl that goes up. Now, it comes up here, and we can start to sort of get an idea of what's happening here. It's a little bit obfuscated because there's so much stacking up here. But when I hit the surface z equals 4, the top of the bowl here will be a circle of radius 2. Whereas the original cylinder, that's a circle of radius 1. So what's happening is I'm seeing the following. I have this cylinder, which is radius 1. I have the bowl, which is radius 2. The bowl comes down, but it's going to stop because what's going to happen is it's going to hit the cylinder. So this is my shape, what it looks like. All right, so that's my shape. Now, we're asked to find the surface area. Let's look at this shape. How many surfaces should we worry about on this shape? Now that's kind of a weird question, right? Isn't there one surface? But oftentimes it's easy to break things into parts and say what's happening on each part. I count 3. 3 is a number to which we shall count. You shall not count to 1 unless you do immediately proceed to count to 3. 4 is just too much. Okay, so one part of the surface you have to worry about is this flat part on the top. Now I claim this one is a really easy part to find the surface area for. Why? Well, what is it? It's a big circle. Subtract a little circle. So the top part, that would be you'd take the following. Area of the big circle is 4 pi, area of the little circle is pi, and so we get 3 pi. So radius 2 circle, subtract the radius 1 circle, and off we go. Now the next surface is the cylinder. So we only see just a sliver of it, but how do you find the surface area of a cylinder? So you find the circumference of the circle, which is 2 pi r. In our case, r is 1. And then you multiply it by the height. Ooh, we didn't find the height, but I'll give it away. It turns out that the height is equal to 3. Now, why do I say that? Well, where do I hit the surface? Z equals x squared plus y squared. And where does x squared plus y squared equals 1 and z equals x squared plus y squared intersect? They intersect at z equals 1. So this part down here, this is z equals 1. That's the height. Upstairs, it's at z equals 4. So the difference between the two is 3. So that gives us 6 pi. Well, what does that leave us with? The work. The slanted part. Okay. Now that's the part where it's like, well, how do we find that? And the answer is we find it using the formula for surface area. So what's the formula for surface area? Well, it's the integral over our region of 1 dSA. That's one way to think about it. If I want to find surface area, well, let me use a different symbol than G. I'll use G for the surface. You're just integrating 1. All right. But what does this really become? Well, what it really becomes is you look down and say, suppose you were looking straight down. If you look down the x-axis, you would see that you'd have 2 circles, one inside the other. And this is the shape that you would see if you were looking straight down the axis. If you call this region R, then it becomes the integral over R. 1 is 1. dSA is your square root of f sub x squared plus f sub y squared plus 1 dA, which becomes the integral over your region, the square root of, here's where you get your f, so 4x squared plus 4y squared plus 1. Now how do you integrate such a thing? What would you do? You'd switch to polar. Because the shape is definitely between two circles. That's a polar type shape. If you see shapes between two circles, you think polar. The other thing is, you have this terrible expression on the inside, 4x squared plus y squared. You're like, I don't want to integrate that. Well, the answer is, switch to polar. And then you're like, well, I really don't really want to do it, but I can do it. Because you introduce that r on the outside, and now everything is not so bad. Use substitution, and away you go. And our time is just about up. Let me just point out one thing. There's something we didn't use on this problem. We didn't use the density. Did we make a mistake? No, it's surface area. Surface area doesn't depend on density.